Within this video, we're looking at ideas involving molecular orbital theory. Within 9.7, the idea of molecular orbital theory was introduced. We learned about bonding and antibonding molecular orbitals and their notation, leading to sigma and pi molecular orbitals, sigma and pi antibonding molecular orbitals. We saw that we could populate energy diagrams, use that to obtain information about the bond order, and begin to connect these to properties like bond enthalpy, bond length, and also magnetic properties. Here's an energy level diagram. We want to be able to add electrons to molecular orbitals and calculate the bond order. We want to be able to make sense of that symbolism, identify molecular orbitals based on their shape, and then be able to place those. Where are the molecular orbitals found in an energy level diagram? These are three different skills. What is your self-evaluation of these? Which ones can you do? Which ones do you have difficulty with? Share your answers, please. Here was an example we worked out. We were looking at the bonding in Li2. I would be identifying where the sigma 1s and sigma star 1s molecular orbitals are found. I would be able to add electrons to the molecular orbitals. In this case, it led to a bond order of 1. I see a total of 4 electrons in bonding molecular orbitals and 2 in the antibonding. If we consider ions like Li2 plus, Li2 minus, both of those end up having a bond order of 1/2, but they get there in different ways. For the cations, we're removing an electron. The electron is removed from a bonding molecular orbital. For the anion, we're adding an electron. The electron was added to an antibonding. Notice in molecular orbital theory, we have information about excited states. This wasn't true when we drew a List structure. It wasn't true in valence bond theory. An important feature of molecular orbital theory, it includes excited states. We saw the role of excited states when we were looking at atomic orbitals. We saw how a photon could come in and excite an electron from the ground state to an excited state. With molecular orbital theory, we'll be able to consider a similar phenomena, but now with the molecule itself. Here's what I mean. A photon strikes an Li2 molecule and promotes an electron from the sigma 2s to a sigma star 2s. What's going to happen to the bond in that molecule? Analyze the energy level diagram. Share your answer. I think the bond order is now 0. I see a total of 3 electrons that would be in bonding molecular orbitals and 3 that are in antibonding. I predict when this photon interacts with the molecule, the bond will break and the molecule falls apart. I'm connecting the bond order with aspects of the bond enthalpy. We've seen that we can have single bonds, double bonds, and also fractional bonds. As the bond order increases, I'm thinking of that as a stronger bond, a shorter bond, and a higher bond enthalpy. A bond order of 0 tells me there is no bond. What about magnetic properties? Where do those fit in? That is something we'll still need to explore. We saw how we could form both sigma and pi bonds that would be both bonding and antibonding when we look at the overlap of p orbitals. An example of that would be in O2. When I populate all of the molecular orbitals, I find that I have a bond order of 2. Here I show the molecular orbitals, both bonding and antibonding, that are formed when I am overlapping the p orbitals in O2. I've placed them in order from the sigma up to the sigma star. Can you connect these symbols? Are you able to recognize those p orbitals and place them on the diagram? Share your response with me. Are you able to make sense of this? Now, we have one series of energy levels when we're using the elements on the left-hand side of the periodic table, and another for those on the right. Very similar, but I just see a slight change when I'm looking at the pi 2p and the sigma 2p. Let's see if we can try a problem. Compare O2 with the O2 minus anion and N2 with the N2 minus anion. How are the anions different from the neutral molecules? Here's how I'm thinking about the N2 molecule. I begin with the electron configuration, and I'm looking at how many electrons I have to add to the molecular orbitals that are formed from the overlap of the p orbitals. I find that I'm adding a total of 6 electrons to those, and it leads to a triple bond. When I move to the anion, the electron is added to an antibonding. This will weaken the bond, reduce the bond order to 2.5, and I would find that I now have an unpaired electron. If I look over there for O2, I'm going to begin with the electron configuration, consider how many electrons I have to add to the molecular orbitals. I find in that case the bond order is 2. When I make it an anion, I'm going to add the electron now to the pi star 2p. This will weaken the bond. The bond order is reduced to 1.5. And I also find that instead of having 2 unpaired electrons, now there is 1. I'm attending to the number of electrons that are unpaired because unpaired electrons will influence the magnetic properties. Here's a very typical question on this topic. You should be able to rank these ions in terms of bond order. You can consult an energy level diagram, but you need to choose the correct one and add the correct number of electrons. Once you know the bond order, you can rank them in terms of bond length or bond enthalpy. By looking at the energy level diagram, you can also determine if they're unpaired electrons. Can you do all of these things? Which of these are you confident with? Which ones do you need more practice? Give me some feedback.